All right, guys, today's lesson is on percent composition. And you guys are familiar with this. You guys have already encountered this even outside of chemistry class. You think about percent composition, maybe in terms of clothing. If you look on the label on your clothing, it might say 50% cotton, 50% polyester. You go to the grocery store, it might say you get some juice, and it might say 10% real juice. And so usually if it's by the liquid, it could either be by the volume, so 10% of the volume would be real juice, and then when you're talking about clothing, other things, a lot of times it'll be by weight. So something you guys are already familiar with. He says, I'm too lazy to buy gift cards, so I'm going everywhere. I'm giving everyone a $10 bill with a note telling them where they have to spend it. All right. So here, you guys, here's a example of a synthesis reaction. You have A and B come together to form compound AB, okay? Notice all the atoms that we start with are the atoms that we end with. So if we have X grams of A and Y grams of B, the question is, how much would compound AB weigh? Hopefully you guys would realize, wouldn't it be X plus Y? Wouldn't you just add those together because of the law of conservation of mass? Whatever you start with is whatever you end with. It's just a different arrangement. Here's a decomposition reaction. So in this case, in a synthesis, small elements come together to form a larger compound. And in this case, the compound is breaking up or decomposing into its constituent elements. So if we had Z grams of AB and R grams of A, the question is how many grams of B would we then have? Well, you guys using kind of the same rationale, wouldn't it be Z minus R? Because shouldn't you be able to add these two together and get the exact same amount of mass of matter as we have here? If you go R and a negative R, when those cancel out, so we have Z equals Z, that's what it would be. So we take whatever the grams of that is, minus whatever that is, that's how much of that would be. You guys, a percent is something that you guys should remember from middle school, even elementary school. It's a very easy concept. In fact, if you guys didn't learn it this way, I feel sorry for you because this is the best way to learn a percent. A percent is nothing more than a part over whole times 100%. Let's say we got a pizza for the class and it had 8 slices. No, you know what? Let's just make it a lot easier. Got a pizza for the class. We broke it up into 4 slices. Let's say someone went and ate, let's say you ate one of the slices. The question is, what percent of the pizza did you eat? Well, you just use this. Percent is part. Well, what's the percent? The part you ate, 1. Over the whole, how many parts were there? So 1 of the 4 you ate. And so then times 100%. And so then you guys can see 1 over 4. The decimal equivalent is 0.25 times 100. Move the decimal over 2 places. And you guys, I think you already could look at that. You ate 25%. But that's how you figure out a percent. So we're going to use that here when we're talking about compounds and elements. For an element and a compound, if you apply the same understanding, if we want to see what percent of a compound weight is attributed to a particular element, what do you think you would do? What do you think would be the part in this situation? Wouldn't it be the element? And what would be the whole? It would be the compound. So basically your percent composition. So what I wanted you guys to see is it's not like this is a whole new formula that you guys are going to have to remember, though you guys should know it, but you can see it's directly related to what you guys should already know in what you were taught about percents. So if I'm getting percent, I just kind of abbreviate this percent composition. Composition means what it's composed of. You get the part, which is the weight of the element, divided by the whole, which is the weight of the compound, times 100%. So you guys, we're going to do a few problems to show you guys how you can apply this. So let's say we have an 80-gram sample of water. Once again, guys, I'll be right back. You guys always get in chemistry to visualize what's going on. Obviously, I don't have to visualize. I can actually see it right here in the classroom. But an 80-gram sample of water, okay? It's analyzed, okay? Usually when we say analyze, you take a compound, you break it down into its constituent elements. And you guys should know water, what's water made up of? You guys know hydrogen and oxygen atoms, right? And it's found to contain 9 grams of hydrogen. What's the percent composition of hydrogen? So they're saying of this water, what percent of the weight is due to hydrogen, okay? So, you guys, what are we going to do? We're going to use our percent composition formula, right? Because it asks for percent composition of hydrogen. So if I want the percent composition of hydrogen, I'm going to get the weight of my element, which is, in this case, it's hydrogen. That's what I'm interested in. I have 9 grams of hydrogen, so I'm going to put 9 grams. So that's the part over the whole. What's the whole? The whole is my water. and water is 80 grams. And then I multiply by 100%, right? And so you do that, and you are going to get, so I go 9 divided by 80. I'm going to get a decimal value. I'm going to multiply by 100, which will move the decimal over 2 places, and it's 11.25. I'm going to just go say it's approximately 11%. So it's 11% hydrogen. So then you guys could figure out. So by weight, 11% of it is hydrogen. So somebody might ask, well, wait a minute. Isn't it water, H2O? So you guys, I would ask you guys, what are the majority of the atoms in the water? Wouldn't you guys agree the majority of the atoms are hydrogen? Because I have twice as many hydrogen atoms as I have oxygen atoms. For every 1 oxygen atom, I have 2 hydrogen atoms. So how can the vast majority of this be hydrogen, and yet the hydrogen only accounts for 11% of the weight? Hopefully you guys would know why that is. Because even though the vast majority of the atoms are hydrogen, what do you know about hydrogen? Its atoms are the lightest there are. What's the atomic weight of hydrogen? 1. What's the atomic weight of oxygen? 16. So each oxygen atom is 16 times heavier than the hydrogen atom. So even though the vast majority of the atoms that make up the water are hydrogen, most of the weight is due to oxygen, due to the much heavier atomic weight of oxygen atoms. Okay. So we use the formula, right? Okay, let's do another one where you're not going to necessarily use you use this formula when it's asking what is the percent composition, but I'm reading this, it's not asking what's the percent composition, it's saying how much hydrogen by weight is there in a 75 gram sample of water. So look, I have 80 gram sample here. Okay, I have an 80 gram sample of water, so I'm going to pour out 5 grams, okay? Let's say about 5 grams. So now I have 75 grams, okay? Now how much hydrogen is there in this by weight, okay? So, you guys, in typical fashion, if we don't just use an equation, we use unit analysis. I remind you guys, unit analysis, remember, it's the endpoint first. What am I looking for? How much hydrogen by weight? So if it's by weight, I want to know the grams of hydrogen. Well, what information do I have to start with? I want to know how much hydrogen I have if I have what? And then we do the start point. And I'm looking for other information. Oh, if I have 75 grams of water. So I start with 75 grams of water. So now at this point, you have to think, how can I get from, now it's called unit analysis because we're analyzing units. How can I get from grams of water to grams of hydrogen? Where is there a link? You guys, really, I was hoping you guys, because there's no more information here. So what kind of thing do we know? Well, you guys think about it. Going back to our original, by weight, what percentage of this is hydrogen? 11%. I pour some out. Now what percent of this is hydrogen? When you guys agree? Trick question, it's still 11%. Now you guys, what percentage of this is hydrogen? It's still 11%. The percent composition of hydrogen doesn't change because it's still water, it's still H2O, it's still in that same ratio. So what that tells us is I can use this information I have here in this. So I want you guys to think, maybe pause it here, how can you use this? How can I bridge a gap? How can I make a link between grams of water and grams of hydrogen using this information right here? Well, think about what a percent is. Here's what I could think. I could go like this. You guys remember, percent is percent. Cent, when you guys think cent, it's 100. It means of 100. So if I had 100, 11 of it would be hydrogen. That's what percent means. So you know what? I'll make up a thing. I'll say, if I had 100 grams of water, guys, how much of it would be hydrogen? Wouldn't 11 grams of it be hydrogen? You see, all I did was I just kind of made up a relationship that would bridge the gap between grams of water and grams of hydrogen. Because check this out, grams of water cancels, and what am I left with? Grams of hydrogen. So then what do? 75 times 11 divided by 100. And I get 8.25 grams of hydrogen. I'm actually, you know what, I should be a better example. I'm limited to 2 digits here, so I should be limited to 2 digits here. You guys remember significant figures? So 8.3. So what did I figure out in this 75-gram sample of water? If I was to break this down, and you know how you can decompose water? You can't just heat it up, because remember, that's just going to make vaporized water. You have to pass an electric current through it. You pass electric current through it, you're going to see bubbles. Let's say I collected the hydrogen. If I collected all the hydrogen, 8.3 grams of it would be hydrogen. And because what is that? 8.3 is 11% of 75 grams of water. All right. So that's what we did. We used unit analysis. You know what? We're going to just do one more here, guys. How much aluminum by weight is in a 300-gram aluminum chloride sample? Okay. So, you know what? This is where you guys could employ your nomenclature skills. It's called aluminum chloride, so you're thinking, oh, okay, Al, it has aluminum and chlorine. And then you guys remember the valence test equals 0. If it's a +3 and there's a -1, wouldn't I need 3 chlorine atoms to balance with that? So aluminum chloride is AlCl3. So hopefully you guys are seeing, and you guys are, if you were able to do that, the knowledge that's being built up. So I want to know if I have a 300-gram sample of this. So what I'm doing is I'm kind of writing down the information I have. I have a 300-gram sample of aluminum chloride. I want to know how much aluminum is in that. Okay? I want to know how much aluminum. So I'm going to set up unit analysis because I'm not asking for an equation. I'm not asking for percent composition. So I want to know grams of aluminum. And I want to know how many grams of aluminum I have if I have 300 grams of aluminum chloride. Now this one's kind of tough because unlike the previous one, you remember we were able to use information from the previous problem. But what else do we have here? This is all I've got. I've got 300 grams of aluminum chloride. I want to know how many grams of aluminum. What you could do is use molar masses. That would give you a relationship. So on a periodic table, I could look up the molar mass of aluminum chloride. So I look it up. Chlorine is 35.5, but I have 3. So what I'm going to do is I'm going to go 35.5 times 3. Okay, it's 106.5. Plus, I have an aluminum atom, which weighs 27. So I'm going to write that down. 133.5 grams per mole. That's the molar mass of aluminum chloride. Well then, you guys, if I need a relationship between aluminum chloride and aluminum, wouldn't I then just look at the, what is the molar mass of aluminum? The molar mass of aluminum is 27 grams per mole. So of the 133.5, 27 is aluminum. You guys see what you're doing? So that's the relationship we could use. I could say, if I had 133.5 grams of aluminum chloride, guys, these numbers once again just came from the molar mass, which we acquired from the periodic table. I could say of that, 27 grams of it would be aluminum. That's by looking at the relationship in the molar masses. So then I just cancel that out and multiply the top, divide the bottom. I get 300 times 27 divided by 133. Oops, messed up, sorry guys. 133.5, and I get 60.7. And so that's what I just figured out. So of my 300 gram sample of aluminum chloride, 60.7 grams of it would be due to aluminum. So if I broke this down into aluminum and chlorine, I would end up with this much aluminum. In fact, that's what one would have to do. Let's say we needed aluminum for aluminum cans, and let's say we had a sample of, that maybe aluminum was found in aluminum chloride compound, and I was able to break it down. This is how much aluminum I could get from that aluminum chloride sample. All right, guys, that's all I got for you. We'll see you next time.